Okay, so today we're going to talk about chemical bonding. Um, and more importantly, we're going to focus on very quickly Lewis bonding theory and how that relates with valence electrons and what the octet rule is and how that plays into covalent and ionic bonding. So, first, let's just write down what exactly Lewis bonding theory is. So, Lewis bonding theory is used to explain how atoms attach to each other to form compounds slash molecules. So, sorry, you might hear my dog in the background. She's being super annoying today. So, it explains how atoms attach to each other or together to form compounds slash molecules. Okay, so Lewis bonding theory is just a way that we are able to kind of make sense as to how compounds arise. That's the most simplistic view of it. Now, the more important thing is valence electrons. So if you remember, valence electrons from, you should have learned this in like environmental science or biology. Those are your outermost electrons, but they don't really explain what they're doing. So those are your electrons that can participate in chemical reactions. Um, Valence electrons explain bonding by way of the octet rule. So we're going to explain that too. But valence electrons explain bonding. And it can explain why molecules take, certain shape. Okay, so now, should have been able to copy that. So we have two kinds of compounds. My pen would work, that'd be great. What is going on? So we have ionic and we have covalent. So ionic, when you have an ionic compound, that means an electron or electrons were transferred. Now if you have a covalent compound, electrons were shared. So I'm going to just draw a quick example underneath. So, and this is definitely not how we're going to be representing this, but anyways, chlorine, right? Chlorine has 7 valence electrons. It's more electronegative. We haven't got into talking about any of that in terms of bonding, but it's more electronegative, and sodium is able to give this one lone electron up. So the octet rule is used to explain how elements want to get to the configuration of a noble gas as it's the most stable. That's like the easiest way to explain it. So sodium is way too far away to be gaining 7 more electrons. It'd be super, super unstable. It'd be too negative. Wouldn't make a whole lot of sense when it could just give one up and be slightly positive. Chlorine is the opposite. It's not going to give up all these electrons. It would be too unstable. It'd be too positive. But it could gain one and be slightly negative. And when you have a positive and negative, think of like a magnet. They attract. So what's happening is this electron is transferred to the chlorine, and you end up with an ionic compound. You have Na+1, and then all of the electrons are around it. This is probably not the way it's represented. I hardly ever use this form in terms of representing compounds, but the brackets mean that it's an ionic compound. Now, as you can see, no electrons were lost. they're still in the compound. These are still, bonded together. They're just not connected. Like, they're electromagnetically connected in terms of the positive and negative force is so strong that even though it ripped that electron away, it somehow bonded them together. Now, for covalent bonds, I'm going to just use methane, which is CH4, to kind of show you. So carbon normally has 4 valence electrons and hydrogen has 1. Now, if you were to simply draw them around, you would know, I haven't gone over the octet rule, but this will make sense in a second. So each line in a covalent bond is 2 electrons. And that line means that carbon has these 2 electrons and hydrogen has these 2 electrons. They're sharing them. Now, we haven't gone over polar bonds or anything where one is sharing it more than the other, but this is a nonpolar compound, so they're sharing the electrons pretty evenly. And that's why we represent it with these lines, is to show that the electrons are shared. Now, if you count 2, 4, 6, 8, carbon has a complete octet. Hydrogen can only have 2 electrons, and I'm going to go over that in a second, but it's got a complete octet. So this would be an example of a covalent compound where the electrons are shared. I just wanted to kind of give you guys a picture of what I was talking about instead of just giving you definitions. Now, all right, the octet rule. The octet rule is simply when atoms bond, they tend to lose, gain, or share electrons to have 8 valence electrons, which is that of a noble gas. And yes, there are plenty of exceptions, so I'm going to write that down. So, noble gases. That's the easiest way to think of it. Because I know we use sodium chloride as an example. And I know in my electron configuration video, I used sodium as an example as well. If it loses that, it's got the same configuration as neon, which is a noble gas. That's pretty much what the octet rule is saying in terms of stability. Now, no scientific rule would be complete without a list of exceptions. So I'm going to copy this over to the next page so you guys can still, write it down. And I'm going to write the exceptions underneath. So exceptions. It's like science and math have tons of exceptions. All right, so 1. Elements that will have a complete set of electrons with less than 8 valence electrons. That would be an exception, such as hydrogen, lithium, beryllium, or boron. Those 4 would be able to complete an octet without having 8 electrons, and that's due to where they are on the periodic table. They're at the very beginning. So okay. So I'll write the elements underneath so we have them. And obviously the reason we are skipping over helium is because it already has a complete octet. It's a noble gas. And then let me draw the Lewis symbol for these. You have hydrogen, and then boron. All right, so Elements in period 3 or higher can have expanded octets. So period 3 or higher may have expanded octets. So that means that they can have more than 8. And that's due to different orbitals opening up, like D and then eventually F. Alright, so I kind of already explained how ionic bonding happens when I was giving you the example. I'm not really going to draw a picture again, so if you need to see that, just rewind. Essentially, the more electronegative atom is going to strip away the lone electron or electrons from the metal. And we'll get into that more when I talk strictly about ionic compounds. So covalent bonds, I'm going to explain, because I did not explain how those work. So covalent bonds. So the central atom for a covalent bond is the least electronegative. And this will make sense in a second. So if you remember from the periodic table, electronegativity increases as you go up and to the right. So that's a good way of kind of explaining or guesstimating what your central atom is going to be. So the only exception to this is hydrogen will never be a central atom. It literally can't. Alright, so pretty much when I write an exception down, I really don't want to see stuff like this on a test. If I'm drawing it, it means I've probably seen it before. So anyways, I don't want to see stuff like that. It's not right. Alright, so remember, electronegativity is the ability of an atom to attract electrons in a chemical bond towards itself. Excuse me. So I'm going to draw CO2. So you don't know the electronegativity values off the top of your head, but you can look at a periodic table. C comes right here and oxygen's over here. So oxygen, even though you don't know the values, you do know it's going to be more electronegative, so it's not going to be your central atom. And it also wouldn't make sense because there's 2 of them. But that means that carbon is going to be your central atom. Now, you don't really know this per se, but say carbon's got 4 valence electrons. Oxygen has 6. And there is 2 oxygens, right? So carbon is trying to have 8 valence electrons. So if you draw a line to each of the single electrons in there to make a bond, you're going to end up with something that's cleaned up to look like this. And when you count these lines and these dots, which are super important to draw, this is called the Lewis structure, Lewis dot structure. If you count the lines, and remember that each line is 2 electrons, carbon has 2, 4, 6, 8 electrons, so it has a complete octet. Oxygen also has 2, 4, 6, 8 electrons on both sides. So everything's got a complete octet. That means if you draw something like this, that's probably not going to be correct. Actually, I'll tell you for sure it is not going to be correct in terms of CO2. Excuse me. Because carbon right now only has 2, 4, 6 electrons. So be aware of that. That's why I told you about the octet rule. Now, I'm going to quickly go over some rules and just kind of explain what all the lines mean in the Louis dot structure. Pretty much each dot is an electron. You're probably going to have pairs of electrons depending on the compound. But all right, so let's go over types of bonds. Actually, I'm going to go to a new page. If you need to copy this, please pause the video and join me in a second. So all right, so actually let's do types of bonds first. So we have single, double, and triple. So a single bond is represented by a single line. Double is, of course, represented by 2. Triple is represented by 3. So that means that it is sharing 2 electrons. This one is sharing 4. And the triple bond is sharing 6. So remember, 2, 4, 6. Each line is 2 electrons. And you'll understand when we get to the Louis dot structure lesson about how to draw and figure out if your element's going to have a double or triple bond. Now, the second rule, make sure to count all valence electrons and ensure you have octets. Super, super important. And the last rule, and this will pretty much do it for the video, is form single, double, or triple bonds to connect the atoms together. Sorry, I was thinking of a word. So form single, double, or triple bonds to connect the atoms together. And there's no real guidance on doing this. I'm going to show you some tricks that'll probably help you see it. But the more and more you do this, you'll be able to just kind of look at something or look at the formula and know if it's a double or triple bond. So, sorry. All of this is dependent on chemical makeup and how much or how each atom gets its full octet. So let's write that down. Depends on chemical makeup and how each atom gets its full octet. And that's pretty much it for the video. I know it's a lot of information, but once you get used to doing this, this is one of the easier things you'll come to find in chemistry. Essentially, just make sure you count your valence electrons and make sure everything has a complete octet. And if it doesn't, that's when you can start experimenting and seeing, oh, maybe it has a double or triple bond. And you're going to get good enough to where you can look at a chemical formula and know what it looks like. But that's pretty much it for the video. If you have any questions, please reach out to me, and I'll see you in the next video.